All right, so now we're ready to talk about generalizing trust region methods to Riemannian manifolds. Okay, um, so you're given a Riemannian manifold with sort of metric. You have a retraction R. Okay, and then you have a cost function. Then you have a current iterate. Let's call it xk. So, so we use the retraction and the iterate to essentially pull back the function f. Okay, so using R and xk, right? We pull back f under R xk. So we have f hat xk, right, which is a map from the tangent space at xk to the manifold M to the real. Okay, and then what it does obviously is that it maps some vector to the function value evaluated when you apply the retraction based at xk to that vector. Okay, so so the Riemannian metric G, right, turns Txkm into a Euclidean space with an inner product okay, and then usually we denote this by angle brackets. Then if it's necessary, it's like we put the subscript xk to tell you where you're evaluating the metric. Okay, so then the trust region subproblem on Txkm, right, is given by the following, right? You want essentially eta k to be the arg minimizer over eta in the tangent space with the property that the induced norm on this is less than equal to, well, induced norm squared is less than equal to sort of the trust region radius, and then the cost function is f of xk plus grad f at xk plus 1/2 hk. Right, then this thing is what I call mxk hat. Okay, and then as before, hk is a symmetric linear operator on txkm, and then one possibility is, of course, the Hessian, and then this is the trust region subproblem. Okay. All right. Okay. So then, of course, you have to, in order to, of course, compute this arc minimizer, you need to have some sort of iterative scheme. It's like to solve this at least approximately, and then we call this the sort of inner iteration, if you will. Okay. So an approximate solution eta k of the trust region subproblem is computed using some sort of inner approximation. Sorry, well, not inner approximation, inner iteration, if you will. Then the candidate for the new iterate is the retraction at xk applied to this eta k. So it turns out that many of the standard iterations, it's like for the Euclidean problem, can be extended to this this case here. So I'm not going to talk about this right now, but we'll be discussing this later on. Okay. All right. So the reason why I say it's the candidate for the new iterate is because it is possible that the difference between what the quadratic model is predicting the cost function to decrease by versus the actual decrease is so dramatically different, right, that you might want to just discard that candidate altogether. Okay, so that's why it's just a candidate as opposed to the actual thing. All right. So let's see. We talk about some sort of notion of a notion of merit, if you will. It's like of how good the model is. So let's just write that in the context of a Riemannian manifold. It's like with endowed with a retraction. Okay. So you consider the quotient, sort of the quality quotient, if you will. And the quality quotient is going to compare the actual decrease in the cost function versus what is predicted by the model. Okay, so this is rho k. So this is going to be f at xk minus f evaluated at the candidate point, which is r xk eta k divided by the prediction, which is m hat xk at 0 minus m hat xk at the arc minimizer of this. Right? So I can write this in terms of the sort of coordinate representation of f, if you will. So I get f hat xk at 0 xk minus f hat xk at eta k divided by m hat xk 0 xk minus m hat xk at eta k. Okay, so this is the quality quotient, if you will. Okay, and if that's large, right, that's saying that the actual descent in the cost function is much greater than what you would have predicted just from the quadratic model. And if it's very small, again, the prediction, sort of the actual sort of descent, it's like in the cost function is much less than what you would have predicted. So if rho k is exceedingly small, then the quadratic model is very inaccurate. Okay, and in that circumstance, what you want to do is you want to reject the candidate, and then you want to reduce the trust region radius, right? So in that case, you reject the candidate, and reduce the sort of trust region radius. Okay. So that's one possibility. So if our rho k is small, but not too small, then what you do is you accept the candidate, but reduce the trust region radius. And then the next possibility is that if rho k is approximately 1, right, then there's a good agreement and of course you accept the candidate, and you increase the radius. Okay, you could have a possibility that rho k is much greater than 1, so that model is still bad, right? But you have a good decrease. But you have a significant decrease in the cost function. And so what you could do is to accept it and again increase the trust region to see what happens, right? So you could accept and increase the cost, increase the radius as well. Okay, so all right. So let me try to formalize all of this now in an algorithm, and then the next step is to then talk a little bit about how you implement each of the various steps in the algorithm. Okay. All right. So this is the algorithm for the Riemannian trust region. The RTR meta algorithm. Okay, so you require the following. So you have a Riemannian manifold. fmg, right, a scalar function f on m, retraction r. Okay, and you have parameters. Let's say delta bar greater than 0. So delta bar is going to be like the maximum truss region radius you allow. There's some sort of initial truss region radius, delta 0, which is between the interval from 0 to delta bar, right? Then you have some sort of rho prime, which is from the interval from 0 to a quarter. And then the input is obviously the initial iterate. X0 in M. Okay, and the output is a sequence iterates. Let's say xk, okay, which is contained in M. Okay, so for k equals to 0, 1, 2, and so on, you do the following, right? So you obtain eta k by approximately solving the truss region subproblem. Okay, which is that eta k is the arg minimizer, right, for eta k, which is in the tangent space to this current iterate with the property that, well, let's just put it eta here, right? So eta inner product of itself is less than or equal to delta k squared, right? And then the model is f of xk plus gradient of f and xk paired with this vector plus 1/2 hk eta eta. Okay, so this is the truss region subproblem. And then you compute rho k equals to f of xk minus f of r xk eta k divided by, all right, and then this is what we call, sorry, m hat xk, right, value by, so you divide this by m hat xk 0 xk minus m hat xk. Okay, all right, so you approximately solve the truss region subproblem. You compute this sort of quality quotient in some sense, right? Then you do the following. So if rho k is less than 1/4, then you update the delta by decreasing it, say, by a factor of 4, right? Else, if rho k is greater than 3/4 and the norm of this is equal to delta k. So essentially what you're saying is that you want rho k to be greater than 3/4, and you want essentially the method to be taking a full step up to the truss region radius. Okay, so if those two things are true, then what you want is to increase the size of the truss region radius. So what this is more or less saying, this condition here is basically saying that, the method might have taken a larger step, if you will, but the maximum of the trust region subproblem is outside the trust region direction. So in that situation, it makes sense for you to expand the trust region radius. If the minimum was already within the trust region, then there's no real benefit in increasing the size of the trust region. Okay, so this is equal to the minimum between 2 times, so it can double the trust region radius, but again, I want to constrain it so that it's no larger than delta bar. Okay, so else delta k plus 1 is equal to delta k, so I don't update it. Okay, all right, so I don't have a lot of space. Let me try to put the rest of the algorithm here, right? So this is to update the trust region radius, and then if you recall, we also had a question of whether or not we were going to accept the iterate, okay? So if rho k is greater than rho prime, which is this sort of parameter I've chosen, then what happens is that I accept the candidate step, so that xk plus 1 is the retraction, xk applied to eta k, else I discard it and I say xk plus 1 is equal to xk. Then this ends the if statement, and then there's a for loop. So this is the for loop part, right? Okay. So anyway, so that's the basic form of the trust region method. It's really not that difficult, right? So there's this trust region subproblem, and of course, it's like in order to actually solve this, it's like there's some sort of inner iteration you have to perform in order to get an approximation of this constrained quadratic minimization problem. Okay, once you have that, you can compute this figure of merit or this quality quotient, and then depending on the value of the quality quotient and whether or not the quality is good, it's like and that you've taken a step right up to the boundary of the, it's like the trust region. If you're in that situation, then you increase the trust region radius subject to the constraint that you're no larger than delta bar for the trust region radius. Okay, so that updates the trust region radius, and then the other thing you do is to decide whether or not you accept or reject the candidate. Okay, and that's the general form of these trust region methods, but then sort of adapted to Riemannian manifolds. Okay, so let me just stop here for now.